Yeah, guys, welcome back to week, 9 of KDD2. We're in the middle of stream mining, data stream clustering, data stream mining. We talked about data streams in general last week, as you may remember. So we're talking about the challenges of stream processing versus batch processing, and we talked about the fact that the classical batch processing mining algorithms cannot be applied to data streams easily because they typically access or require multiple access to the raw data, where we have in the data stream scenario, we only have the one-shot scenario. We talked about aging models, and we talked about how to store the history of the data, and we talked about things that can happen during stream evolution, especially that patterns may also change over time. And then we talked about clustering in data streams. So we had these adaptive approaches that typically transform the k-means algorithms into single pass algorithms. Then we had some kind of offline-online approaches where we have a two-step approach, the online phase, which is the stream maintenance or the stream processing, where summary structures, so-called microclusters, are summarized or are kept or maintained during the stream evolves. And the clustering actually can be done offline on those microclusters, giving or resulting in a macrocluster clustering, which is potentially only an approximation of the original pattern. But anyway, as long as the microclusters are accurate, then the macroclustering will also be quite okay. And we also talked about a special instance actually of the offline approach, which is the continuous grid-based clustering approaches, which just use data grids or grid units for summarization. And we stopped before doing change detection. So change detection will be the first subsection of today, which is amazingly short, but anyway, that's just a brief overview what can happen, and some pioneering work here in change detection. So the basic idea here is that we want to detect and also differentiate between different types of changes, not types of patterns now, but types of pattern changes. And basically there are four different types of changes. So the disappearance of concepts, the migration, change or drift of concepts, patterns. So concepts and patterns are used interchangeably here. The merging of existing concepts, and the splitting of groups versus newly emerging clusters. And you see here different things that happen over time here on the x-axis, on the virtual x-axis, so to say. So here we have a kind of drift where those clusters somehow drift, at least the four clusters on here at the border drifts towards the border, as you can see here. The middle one more or less stays the same. The middle one grows here, then from this time slot to this time slot, and then we have a split into several clusters here. Novelty, which is this one here, and a slowly disappearing concept, or several slowly disappearing concepts here, and probably also here. So you see that there's a moving or migration, a drift from the middle to outside of those four clusters, and then these four clusters disappear as time goes by. We want to detect those changes actually. And there is, as I told you before, this kind of pioneering work here by Myros Pilopoulos and colleagues called MONIC, Modeling and Monitoring Cluster Transitions. So we're still in the clustering subsection. MONIC does not assume a particular cluster model, but claims to be model agnostic. So MONIC just looks at what is happening to the clusters and what is happening to the concepts in terms of those four different cases. And for detecting and differentiating and also representing those different types of changes from time slot to time slot, MONIC especially proposes a cluster matching for different time points, because otherwise, if you don't know if this cluster, for example, matches this cluster, I mean, they might be slightly different because time went by during those two time slots, so they might be a little bit different. So how do you know that this cluster here in this time slot or matches or represents this cluster from the previous time slot? Yeah, so you need a kind of cluster matching concept, and this is what MONIC actually proposes. So let X be a cluster at time slot X and Y be a cluster from the set of clusters at time slot Y, which is later. Yeah, so Y is TY is happening later than TX, and this what is it, Xi or Phi or Psi or whatever of Y. I'm very bad in this Greek letters. You might already notice that. Anyway, so this here denotes this all set of clusters at time slot TY. Yeah, and X is one particular cluster from the set of clusters at time slot X, so CX or whatever. Yeah, and now you can compute the overlap between X and Y like this one here. So you just sum up all the points in X, not union, intersect Y, yeah, times the age of O, yeah. So all objects that are in the intersection of X and Y times or weighted by the age of this O here, divided by the entire number of X. Yeah? So this is somehow the relative number of objects O from X that are also in Y, so to say. Yeah? And we say that Y is a match for X if this matching we denote this by match X, then the set of clusters at time point Y is Y. This particular cluster Y here is a match of X, denoted by this one here, subject to a threshold, obviously, which should be between 0.5 and 1. If, now this is the important part, so Y is a match of X if X is the cluster with the maximum overlap computed here, but the overlap must be at least tau. Yeah. So if Y is the cluster with the maximum overlap to X, but the overlap here is below tau, then X has no match actually. Yeah. If there's no, that's written down here. So if there's no cluster in the clustering at TY with an overlap of at least tau, then the match is empty. Yeah, so X has no match. So the matching is not unique. Several old clusters can be matched with the same new cluster. So in this direction, it's not unique. Yeah, so it's not surjective or objective or whatever. Yeah, injective. I'm sorry. Okay. Anyway, so this is the overlap concept. Yeah, so you just compute the overlap, and if you take the cluster with the highest overlap, if this one has more than 50% in common, obviously, so the threshold is 50% to 100%. So if the overlap is more than 50%, you take this one as a match or as the matching partner. If the overlap with the one which has the highest overlap is below 50%, you say that this cluster X has no matching partner in the time slot, in the set of clusters at time slot Y. Okay, and now MONIC basically proposes a lot of different cluster or pattern evolutions, basically following this idea here, or the guys listed here, the points listed here. So cluster survival, cluster splits into multiple clusters, clusters is absorbed, cluster disappears, a new cluster has emerged, and stuff like that. And they also propose some specific notation and the corresponding indicator, which is based here on this match concept, which is again based on the overlap concept, as you see here. This is the external transitions of a cluster, and there may also be internal transitions of a cluster, which means size transitions. So the cluster may shrink or expand. Compactness transition, the cluster may become more compact or less compact, so diffuser. Location transition, so shift of center or distribution, and also no change, of course. So all this is formalized in this paper here, as I said before, the authors also propose a notation and basically formalize it here with these indicators here. And this is, as I said before, a pioneering approach, and people use that still a lot to describe cluster transitions or pattern transitions, concept drift in clusters. And that's it for today, or not for today, but for clustering, for this short clustering part. So here is the summary of clustering, of the stream clustering part, of the whole stream clustering part. It's a very important task given the availability and width, breadth of data streams nowadays, of course. So stream clustering algorithms, as you have seen, typically maintain a valid clustering of the evolving stream population over time. And there are two generic approaches: online maintenance of final cluster model, or online summarization of the stream and then offline clustering of the final model. We got to know different window models. So these are the aging models. Some word just to mention: the evaluation of stream clustering algorithms is not straightforward. You probably know some existing measures for static data or for static clustering algorithms, so for batch clustering algorithms from KDD1, and this is also not trivial to do. So the evaluation of clustering is not trivial to do per se, and now since cluster evolution, pattern evolution may come into place, this is even more complex. We here in this lecture we just glanced the surface, so to say, or touched the surface. So there are more specialized approaches, especially for text streams and for high-dimensional streams. So just that you know, there is a lot of more stuff going on, or which has been proposed in the literature on stream clustering. Okay, so here are some selected readings on stream clustering, and if you want to know a little bit more on that. And then in the next podcast, we will talk about classification, or in the next, in the remaining podcast this week, we'll talk about classification in data streams. Stay tuned.